Gesture elicitation studies aim to find common gesture patterns in a pool of gestures proposed by users. Visualization tools have been recently introduced for visualizing the resulting spatial-temporal data. However, previous tools have been limited to 2D projections of gestures performed in 3D space. In this video, we present GestureExplorer, a virtual reality tool for exploring gesture data in 3D space. GestureExplorer supports spatial understanding by representing gestures and 3D skeletons overlaid with motion trajectories. Along with multiple 3D visualizations and coordinated 2D views, GestureExplorer turns the surrounding immersive space into a part of the analytical process for better understanding of gesture data. Let's follow the perspective of a gesture analyst exploring a gesture dataset. In the start, GestureExplorer loads the entire dataset into one big cluster. The analyst organizes the gestures using PCA and turns on the overview map to observe their positioning. It finds that the gestures can be roughly distributed into 3 clusters. GestureExplorer supports k-means clustering with multiple rationales. In this case, it sets the k-value to be 3 and chooses PCA as the clustering rationale. The resulting 3 clusters are represented by bubbles with 3 distinct colors. The bubble size encodes the number of gestures contained. Embedded in each bubble is the cluster's average gesture represented by a skeleton with its motion trajectories. The analyst notices some overlap between the clusters and decides to manually adjust them. The analyst uses the Change Cluster feature by selecting some gestures and assigning them to another cluster where he thinks they should belong. This will trigger a recalculation for both the initial and the current cluster. The analyst now wants to find out which cluster has a higher consensus for the entire dataset. He switches to the global arrangement, which positions gestures and clusters relative to the consensus with the entire dataset. A cluster with a shorter distance to the star on the ground origin suggests a higher consensus. The analyst locates the closest cluster and decides to further refine it. He expands the cluster and switches to the local arrangement. The gestures are placed around their respective clusters based on their similarity with the average gesture of that cluster. With the help of the overview map, he notices a few gestures that are far away from the cluster. The analyst marks them up and switches to the lineup arrangement, which offers a sorted view based on the local similarity. The analyst checks the line for outliers near marked gestures. It makes a comparison between each potential outlier and the average gesture to decide if it should be excluded. The analyst has multiple ways to inspect and compare gestures. It looks at the motion trajectories for any obvious differences. Freehancer small multiples views provide normalized keyframes of each gesture to allow the identification of motion trends over time. You can also explore the gestures by viewing the animations. Alternatively, the analyst can play back the animation with the VR controller as well as a second animated view overlaid on small multiples. Finally, the analyst creates a new cluster and assigns the confirmed outliers to it. He stacks all the remaining gestures in the cluster and turns on the heat map, which uses additive blending to highlight areas with the greatest amount of motion. The heat map view shows a distinct bright patch, indicating high consensus among the stacked gestures. The analyst wants to focus on the motion of the left hand, so he filters out the unnecessary trajectories to reduce visual clutter. To this point, the analyst can be confident that the elicited gestures in this cluster are in high consensus, and a representative gesture pattern could be derived from the cluster. GestureExplorer can also be used to validate different clustering rationales. In this example, the analyst wants to see the difference between clustering with MDS and with DBA. He initializes a clustering session with the same value for k, but each with a different rationale. Each clustering session results in a 2D panel. This panel shows an overview of all gestures. Any selections made in the panel are linked with the corresponding 3D gestures. The analyst snaps the panels together for comparison and identifies a few disagreements. He can then conduct further exploration to understand the reasons behind them. GestureExplorer allows designers to propose their own gestures and look up similar proposals in a dataset. In this example, a designer proposes a gesture and finds several similar gestures. This suggests that his proposal could be easily guessed, learned, and possibly preferred by the general users. We evaluated GestureExplorer with 2 user studies. The results showed the promising ability of GestureExplorer in supporting the exploration and analysis tasks of gesture data in practice. Please refer to the paper for further details.